Hello, dear colleagues. This is my fourth presentation, and my name is Professor Sergey Shityakov. I'm head of the Cheminformatics Scientific Group at the Infochemistry Scientific Center, the ITMO University. And on this lecture, I would like to give a couple of words on the algorithms and what are the algorithms we are using in particular for the chemoinformatics purposes and how they are implemented to analyze the chemical space. There are different algorithms which we are using in chemoinformatics. They are much more than here on this slide. They're still developing, and new algorithms are coming up every day, or maybe every month. These are algorithms which are not new, but some of these algorithms are also still in the active development by our group. And what are the particular algorithms which we are using? First of all, we are implementing genetic algorithms, Monte Carlo techniques, simulated annealing algorithms, some algorithms which are less common, such as induced heat algorithms, Voronoi tessellation techniques, hidden Markov models, and so on. The genetic algorithms are algorithms which are not new but still very useful for chemoinformatics, for the processing of the molecules, and they are highly useful in terms of the molecular docking technique, such as autodock or autodock Wiener pipelines to analyzing protein-ligand interaction for different chemoinformatic bioinformatic purposes. And genetic algorithm is a subclass of heuristic search algorithms based on the principles of natural selection, and is a type of the evolutionary algorithms, where we have some chromosomes, which we are calling the virtual chromosomes. They might represent the molecules, and by applying the natural evolution, we could try to optimize either the generation of different molecules, or we could optimize the interaction of these molecules with some proteins we might think are useful for the inhibition or the stimulation in order to treat some diseases, such as neurodegenerative diseases. And on the slides, you can see some virtual chromosomes represented by the either they're bit chromosomes, either zeros or ones. We're calling them parent chromosomes, and by applying some molecular techniques like crossing over, which we modify from the natural selection, we could generate some child entities such as zeros and ones, and these child entities would bear the information from both of their parents. This algorithm is quite useful, and they are not really very time consuming, but still not good to implement them if the researcher has a extremely huge database, such as millions of different substances, because these algorithms are still not very fast in comparison to some algorithms like pharmacophore algorithm or similarity searching algorithms and different filtering algorithms. We could also change different parameters using genetic algorithms such as mutation rate or crossover rate. And when we are changing these mutation rate, we could also decrease the similarity of different substances, because the more mutations we introduce into the molecules, the less similar the molecules would be produced from this procedure. The algorithm is primarily designed to find high-quality solutions for the optimization and the search task by using operations borrowed from the wildlife. The other algorithm is called Monte Carlo technique, and this algorithm is based on the metropolis criterion, which I'm not going into details due to the time frame. And the Monte Carlo algorithm starts from the initial setup. Then the researcher specifies some moves of the molecules, and after that one could calculate the local energy of the molecule. And the move of the molecule might be accepted or rejected on the basis of the energy of different molecules. Either the energy is decreasing or increasing, and all this is analyzed by the probability function, which is quite useful, such as the scoring function. So one could use this probability function, Monte Carlo probability function, to find the candidates which are more suitable in terms of the energy, and therefore we might assume that if the energy is low, then probably the binding is also better, or the stability of the molecules is also going to be better. The third algorithm is called the simulated annealing. It's at some point similar to the previous algorithm. The only difference is it's using some kind of a temperature. It also using the random run, where one could specify the positions, orientations, and conformations of different molecules, then make the random state changes, accepting uphill moves with the probability dictated by the temperature. And after that, one could reduce the temperature after each move. And finally, we could terminate this process when the temperature gets very small. By implementing an algorithm, we hope that we could reach the global minimum, which represents the optimal state at which the ligand would interact with some target proteins, therefore representing the lowest energy of interaction. These algorithms are using the scoring functions. There are different scoring functions. Here I could subdivide these scoring functions into three classes. First is a force field based scoring function, which is the standard force field scoring function. The second is empirical functions. Then one could also change this that parameters using some kind of a hybrid scoring functions as a combination of different functions, like force field scoring function plus empirical scoring function, and so on. So on this slide, as an example, one could see that the functions are usually represented as a Gibbs free energy of binding to evaluate different binding affinities. And we could also implement not just the scoring function, but some parameters, structural parameters, to calculate entropy values and how these values correlate with the Gibbs free energy of binding. And this is all for the algorithms and the scoring functions. And thank you for your attention.